Welcome back. Another lecture, this one on sound and audio. This is chapter 7 in your book, and let's get going. There's a lot of ground to cover here. We're going to talk about what exactly is sound, the types of microphones. We type microphones by their pickup pattern, and we also type microphones by their construction. We're going to look at some microphone accessories. What is audio? How is audio different from sound, right? Go over some of the digital fundamentals. We covered that earlier in the video portion, but we'll go over it again for sound. And then consoles and their parts, specifically the parts of our console there at De Anza, and some recording. So first off, what is sound? All right. We can have a big discussion about what is sound, but essentially what sound is, it starts off as a vibration, whether it's your larynx, your vocal cords vibrating, or the string of a guitar or of a violin. That's where the sound emanates from. Sound starts with a vibration. Now, that sound doesn't happen unless it's in some sort of medium. So like maybe it's in a medium like gas, like air, and it causes waves in that medium. Now it can also cause waves in these other mediums. If you have ever listened, if you've dove into the bottom of the swimming pool, right? Listen when you're in the swimming pool, you can definitely hear sounds in the bottom of the swimming pool. People splashing around, people walking on the bottom of the swimming pool. And if you ever have had a neighbor that's given a party, you know that sounds transmit through solids, and the mitigation of sound, through solids, like in studio design, is a big deal. How to get soundproofing and things like that. But the vibration causes a wave in some sort of medium. That wave strikes membranes in the ear, so it ends up going right there in the ear, and in your ear, it's translated into some sort of bioelectrical signal in the brain. So I'm not going to ask you any of the parts of the ear, but I want to show you the ear just to show you the process. The sound waves come in here, they strike the eardrum, and the eardrum vibrates, and that eardrum presses on these three bones in your inner ear. All right, so we've taken this acoustical energy and translated it now into a mechanical energy. All right, so we get this mechanical energy happening, and then that squishes this device this organ in your inner ear called the cochlea. All right, the cochlea is an organ that's filled with a fluid, and in the fluid, there's suspended these little hairs called cilia. Right. And so when when the sound comes in and translated mechanical energy here and then squishes on the cochlea, right, those little cilia start moving too, and they start waving around too because of they're dancing around in that fluid. Now, if you've ever noticed, if you ever plucked a hair, like an eyebrow hair or any one of your hairs in your arm or something like that, you'll notice that it hurts, right? And that's because there's nerve endings in the follicles, in your hair follicles, in the base of your hair, right? And the same thing happens in the cochlea. It's not like it hurts, but there's nerve endings in the base of the hair follicles of the cilia in your cochlea, and that fires off a signal that goes up right here, the nervous system, into the base of your brain. It gets to the base of your brain, and then somewhere in the higher parts of your brain interprets that as sound. All right. So we've taken the acoustic energy, turned it into a mechanical energy. That mechanical energy is then turned into a electrochemical signal in your brain. All right. And this is not unlike how our microphones work. I'll show you a picture of that in a second. Now, what are sound waves? I mean, maybe you've seen a wave like in some sort of editing program, right? You've seen that wave that you use in in Pro Tools or Adobe Audition or something like that, or Premiere, those aren't sound waves. The waves that go through the air, right? These sound waves are longitudinal. That means that they go like that, right? They go longitude is in one direction or the other, right? And they're waves of compression and rarefaction. So the actual air molecules, there's parts of the air molecules within the wave where there's fewer molecules, air molecules, and those are the rarefaction areas, right? I used to live in Colorado, and they talk about going to the rarefied air up in the mountains, and that meant that the air up in the mountains had fewer oxygen, it had less oxygen in it because there are fewer molecules in that, up at 14,000 feet. Right. So rarefaction, rarefied air, that's the kind of the thought. And compression just means that we've compressed more molecules together. So that's what the waves look like. This is where you see the waves, and then this is the area where in between the rarefaction is the area in between the waves. All right. So a sound wave, longitudinal wave of compression and rarefaction. We have this effect called the binaural effect, just like we have 3D vision. Well, we have 3D hearing too, because what happens is that the sound comes into your ears, and the sound wave here hits this ear before it hits this ear. And your brain can put together that information there and go, well, the sound must be coming from over here. All right. And so we do have stereo imaging. We have imaging of sound when we're using stereo, when you have, because of your stereoscopic hearing, the binaural effect. Okay. And this is what also happens when we have stereo speakers. And then we got surround sound speakers and all that kind of Dolby Atmos, and that gives us all this imaging too. So microphones are transducers. It just means that it converts energy. It converts the acoustic energy into electrical energy. And remember, here in the ear, we took acoustic energy, converted it into mechanical energy, and then it went to this electrochemical energy. Same thing. We take the sound, the acoustic energy, it hits this diaphragm in the microphone and converts it to a mechanical energy. And somewhere in the electronics here, it converts it, and I'll show you pictures of that in a couple of panels. It converts it to an audio signal or electrical energy. Now, microphones are low impedance devices. Impedance is sort of like resistance. Resistance resists the ability of current to flow. Impedance, low impedance, means that current is allowed to flow, is allowed to flow because it is not impeded. It is not restricted by the circuitry. Okay, so a low impedance circuit means that it more freely allows the flow of electricity, and therefore the audio signal. All right. And these devices are, our cables, and our microphones are less susceptible to hum and interference, the low because of their low impedance, and they can handle long cable runs. You don't think about it, but there's between the microphone and the audio board upstairs is a lot of cable, right? It has to get from the equipment rack into the microphone, into the board, into the audio board, and there's a lot of cabling that goes with that. So we can also classify microphones by their pickup patterns. Okay, so we'll classify them by pickup patterns first, and then we'll classify them by their construction. So we have omnidirectional microphones. And that means that it's a non-directional pickup pattern. It can pick up sound from all around the microphone, no matter where the sound comes in, even from what looks like the back of the microphone. It will pick up sound from the back of the microphone. And we use this when the source is not going to be particularly close. We can use omnidirectional microphones. Or excuse me, when the source is close, we use those. So most of our lavalier mics. The lavalier mics are the ones that we wear, right? Those are omnidirectional microphones. Because we're close up to the voice, and the omnidirectional pickup pattern works well. They are less prone to wind noise, but I would pick a different type of microphone with the right kinds of accessories before I go to an omnidirectional microphone. They're good for wide sounds, not necessarily stereo sounds, but sounds like if we want to pick up a sound over here and we want to pick up another sound from over here, and we only have one mic choice, well, an omnidirectional microphone might be a good choice because it can pick up sounds from all around the microphone. Omnidirectional microphones are good for crowd mics in sporting events. Okay, so if you want to pick up the sound of the crowd, you put an omnidirectional microphone far enough away from the crowd so that we're not picking up specific audience members, right? Put it up a little higher or farther away, and it's an excellent crowd mic for a stadium or something like that. Now we also have bidirectional mics, and those are good for interviews with two persons. So what we're looking at here is a polar pickup pattern, right? When we're looking down at the top of this microphone, right? So here's the microphone, we're looking down at the top of it. These are nodes, so this is where it can pick up sound. These are nulls, where it doesn't pick up sound as much. And so if we had a guest and an interviewer, that'd be great for a podcast or something like that, right? So we could use a bidirectional mic. And in the early days of broadcasting, there were a lot of bidirectional mics that were used. And later on, we got to the point where we could give everybody a microphone and a lav or whatever. And so we see fewer bidirectional mics now in broadcasting because we can give everybody a microphone. And we see a lot of these microphones everywhere, the cardioid mics, all right? And cardioid pickup pattern, right here, this is the cardioid pickup pattern. Cardioid, you want to think of it like heart, right? The carotid artery, they're, cardiovascular. And if you look at the pickup pattern, it's like a heart, right? Like that, it's kind of like a heart, right? Sort of. Right? So that's where we get the cardioid pickup pattern. And it has a front end and a back end of the microphone. So this would be the front end, right? And this would be the part where it doesn't pick up as much. And so it rejects more off-axis high frequencies, right? So what happens on a microphone when you get a directional pickup pattern, you have an axis. Right. We'll talk about the z-axis in our cameras, right? Well, this is the axis on the microphone. And so this is where the where you should put your guests, point it towards the sound that you want to get. And then this would be off axis because, this is off the main axis of the microphone. Now this is a cardioid pickup pattern, right? But then we get into shotgun microphones. And even though the pickup pattern doesn't look like a cardioid pickup pattern, it is considered a cardioid because of the construction of the microphone, of the electronics that are in the microphone. They just mess with the electronics to take this pickup pattern and make it really longer out here, right? And so that's what you get right here with the hypercardioid, supercardioids. I've even heard some people have a class of microphones that are just shotguns that are even more than the super or hypercardioids. All right, so now we can also classify our microphones by their construction, by the way that they do their transducing elements. Remember, we're converting energy. So these are magnetic induction devices. There's some sort of magnet or electromagnet that's involved in turning the acoustic energy into electric energy, right? And the dynamic microphones are one of these magnetic induction types of microphones. What happens is sound waves come in here, and what is happening here is that this is an electromagnet. All right, we have a coil of wire that is wrapped around a magnet right here with a north pole and a south pole. And when the sound waves come in here, the diaphragm vibrates along with the acoustic energy, the sound waves that come in. And then that means that this coil of wire will vibrate as well. And then that changes the electrical signal that's induced because of the magnetic field here. All right. And so this is a dynamic microphone. Here's a couple of, the Shure SM58 and the Electro Voice 635A, a couple of dynamic microphones right there. And the dynamic microphones are really known for their sturdiness, for their ability to take a hit. So they give you a really good sound, but they're a good field mic. And this is why we see a lot of TV field producers using dynamic microphones. If you see a reporter in the field, they are using a dynamic microphone, most likely because they can hang on to that and throw it in the back of the van, and it'll take a good it's a good sturdy microphone. The other type of microphone we use TV primarily is a capacitor, or some people call it a condenser microphone. Okay, and you can see there's two types right here. This is a shotgun microphone, right? That you would use on a boom, right? And then this here, and this is the microphone right there. Right there is a lavalier microphone. Now this shotgun microphone, this would be a hypercardioid, right? And this lavalier microphone would be an omnidirectional microphone, right? But they're the same type of microphone as far as their construction. They're both capacitor microphones. And the difference in these microphones is same sort of things going on here. This acoustic waves come in and they hit a diaphragm right here. But instead of it wrapped around instead of having coils of wire wrapped around a magnet, what we have going on here are two charged plates, right? And so when the sound wave comes in here, it makes this diaphragm move. And since these plates both have a charge, it makes that electricity, that electrical charge between them, the capacitance between them change. Right? The magnetic field between them changes, and that's what is interpreted as a signal. So the signal comes out here. Notice too that there is a battery, right? So to make the capacitor microphone work, there has to be a battery involved, all right? It needs some sort of charging, needs some sort of electricity. So in our lavalier mic, we have a battery in the lavalier mic. And in our shotgun mic, there might be a battery right here. All right. Now there are some shotgun mics that have a thing called phantom power, and they would get the power off of either the mixing board or off of the recorder. All right. So they don't have a battery in here, but they have a cable that's wrapped up in their XLR cable that goes to the recorder, and it gets power from that. Right, and then here's just some more of the mic types. These are handheld, right? So here's that 635A dynamic mic, right? And these are like the handheld microphones that we have, right? But these are also wireless mics. We'll get into wireless mics in just a second. Here are the lavaliers mics. In fact, this is the exact type of microphone that we have, but this is a different type of microphone, but it's still a lavalier, different brand. Shotgun microphones right here and here, right? So I got to warn you, all right? This picture is a screen grab from a sales brochure kind of thing, right? And they want to show how cool this video camera is, and it also has a shotgun microphone here. But if you're using a camera like this in the field, don't use this microphone. Don't use that microphone. Either take one of these microphones, take a lavalier and put it on your subject, right? Or use a shotgun mic, because this shotgun mic here is highly directional. And when it's out of the frame up here, it will pick up your subject. Don't use the shotgun mic here because it has to be put a distance away from your subject, and you're going to get all of this wind noise. You're going to get the street noise from out in front of the Capitol building and all of that kind of good stuff. You're going to get reflections off of sidewalks. So this is not a good one to use that for in this application. This is just good to sell the camera to somebody who's going to buy it. So talked about wireless. We have wireless mics in the studio. So this is where the microphone plugs into, right? And then the microphone gets put on the subject. And in here's the battery. The battery packet goes in here. And this is the antenna, because the battery is not only powering the microphone, it's also powering a transmitter right here. And that transmitter transmits through this antenna and gets picked up by the shark fin antenna. I think I've pointed it out in the studio, right? Actually in the control room, right? And it gets, so signal goes from this antenna, gets picked up by this antenna, and then goes up to the rack and the receivers. And these are the receivers that we have in our audio booth, right? And there are 8 receivers for wireless microphones, and we can either use 8 different, when they're all working, we can use 8 different lavaliers or 8 different handheld mics, or a combination of the 2 that gives us 8. And it tells you on the front of the unit of the receiver what's happening if now it's not turned on, right? So when it is turned on, you get a little battery indicator. So it's good to make sure that the batteries are working. And if the battery indicator looks a little low, well, then go down to go down and change them in the studio. Go change the batteries. This tells you how much audio is coming through. And then these are the transmitters here, or it shows you the signal strength coming off of the transmitter. What happens in our professional grade microphones, wireless microphones, is that it's transmitting on an FM signal, right? And it has 2 FM signals that it transmits on. And at any given time, the system figures out which is the strongest signal to take. And so it will use the strongest signal. And if for some reason there's some interference that happens and that signal gets weak, but the other signal is stronger, then it'll flip to the B one or the A one or wherever it's using. So this one thinks that the B one is the best one, so it's using this, but if A becomes stronger, it will flip over to the A signal. All right. And that's just to help for the robustness of the transmitter signal. I've worked semi-professional microphones, wireless microphones that didn't have this setup. They only had one signal, right? And those are tough ones to work because they get interference, right? And there's all sorts of things that can cause interference to your wireless signal. Cell phone traffic, yes, can cause interference. If that happens to us, we may have to go into airplane mode on our cell phones. Sometimes I go into airplane mode just because I don't want to get, I don't want my cell phone searching for a signal for 4 hours and it depletes the battery. But sometimes I don't want it to interfere with our receivers too, with our wireless mics. Two-way traffic from first responders can also interfere. And then also there's all sorts of two-way traffic and microwave traffic and cell phone traffic that just is in our environment, and that all can interfere with the wireless microphones, right? Also, reflective surfaces can also reflect on our receivers and give us interference. So we have to watch out for these kinds of things. Now, we're in a very controlled environment at De Anza in our television studio. So we've kind of dealt with all of those kinds of sources of interference. So the only real interference that might give us a problem are sometimes cell phone traffic, but it's rare, but it can happen. The two-way traffic and the reflective surfaces, we've dealt with that in the construction of our facility. So that's a good thing. But when you're on the road, when you're in the field, you'll have to be careful of those kinds of things. Some accessories, there's shock mounts, and the shock mount is basically a rubber band kind of thing. You put the microphone in these rubber bands, that's strung inside here. And so that if you're moving the boom pole, right, you're not going to get rumble in your microphone. And then here's a type of windscreen known as the dead cat. For some reason, the randomness of the fur on this helps for windscreens, but maybe you've seen a hard one that goes around this called a blimp. I'll have to get a picture of a Zeppelin or a blimp that goes around this, right? And there are also windscreens. These are windscreens that go on the microphone. These are pop filters. Sometimes your microphone is not rated for a windscreen that you can put on it. So when that is the case, you put a pop filter up there. And if you have your microphone right here, you put your pop filter there, and then people can talk or sing right there. Because if you put a windscreen on the microphone, it would change the dynamics of the microphone. So some microphones aren't rated for windscreens, but some are. You have to check your documentation to find out. A couple more accessories here. These are stands. So these are floor stands, right? Because they go on the floor. This is maybe a desk stand. These are desk stands, right? These are desk stands. And then this device here is a boom. When it goes horizontal, that is a boom, right? Just like in film production, we have a boom operator, and that stick that the shotgun microphone is mounted on is the boom pole, because it's held in an orientation kind of like that. So these are microphones and accessories, some things about sound, but what is the difference between sound and audio? Okay, at some point in the back of the microphone, we're changing that sound that comes in the front of the microphone. We're changing it into audio that comes out the back of the microphone and goes down that XLR cable, right? And audio is just the electronic representation of sound, or replication of sound. And you may have seen waves like this. This is an analog wave. Now, you may have seen this on a digital device. That's okay, right? But the analog wave gets its name because it's analogous. It's an analogous representation of the electronic components of an audio wave. Used to watch a lot of Mythbusters, and they would do a thing where they would want to test how it, like a truck tire, if a truck tire blew up and it hit you, how would it affect you? Well, you can't throw truck tires at human beings. They'll get hurt, right? So what they would do is they take a ballistics gel and make a form of Grant, right? One of the guys that worked on Mythbusters, and they would fill this mold of Grant's top, of his head with ballistics gel, and they would flop that out there, and you'd have this ballistics gel of Grant's head, and that would be an analog of Grant, right? It's just something that's analogous to Grant, and then they can shoot truck tires at Grant's analog so Grant doesn't get hurt, right? That's what an analog is, all right? It's a representation of, in this case, the electrical components of an audio wave. And here are the components of an audio wave. We've got amplitude, right? And amplitude is usually measured in some sort of polar fashion, a plus value and a negative value. In this case, it's voltage, plus voltage, and negative voltage. All right. So it's a measurement of polarity, the amplitude is, and the other measurement is wavelength. All right. And wavelength is a physical measurement of distance. It's something that we all relate to because you can get out your ruler and measure it, right? So we can measure them in meters, or we can measure them in feet, or something like that. And what you're measuring is one cycle of the wave. So if we take this wave and we get one cycle in the positive, right? And then one cycle in the negative. When it gets back to the positive, to the line there, then that's one cycle. Now, if we started measuring it from here, that's a half cycle in the positive, okay? And there's a full cycle in the negative, right? So we have to go another half cycle in the positive. So if we started our measurement here, the end of that wavelength would be here. But classically, we do it from this to that. Right. So there we have amplitude and wavelength. Well, then, so what does that help us do? Okay, so we get our analog wave. There's these guys. One of them was Heinrich Hertz, who came along and thought, well, there are different pitches of sound. I wonder how that works out with our wave model. And what he figured out was that if you take that cycle and you divide it by a unit of time, you get an actual pitch. All right. And so the frequency is the number of cycles per unit of time. We perceive it as pitch. All right. It's not necessarily pitch itself, but that's good and close enough for us. Okay. The frequency is number of cycles per unit of time. So 1 cycle divided by 1 second equals 1 hertz. So remember, it's cycles divided by time equals the frequency. And the frequency is perceived as pitch, right? And here's a keyboard, and these are the bass notes on the keyboard, and these are the treble notes on the keyboard. And you'll notice these are the frequencies. I know it's a little grainy here, but the frequencies on the keyboard, the lower frequencies have a lower value, right? 27.5 hertz. And the higher frequencies have a higher value for 4186.1 here for this C note up here, right? So it is a higher frequency value. All right, so frequency perceived as pitch, lower frequencies, lower pitches, higher frequencies, higher pitches, right? Okay. All right, so now we're going to take this analog wave and we're going to convert it into digital information. So we can, record it on our computers, right? And pass it around the internet or do whatever we want to do with it, right? And so what we do is we sample it. We talked about sampling for video, and it's the same thing. All right, I'm going through it again a little bit more in depth. And so what we do is we sample the wave. And what we're doing is we're sampling the voltage of the wave at any one moment here. All right, and then we'll take that sample and we'll represent that sample as some sort of binary information. And in this, this case, it's on is that 1 and 0 is off pulses, right? So here's on, off, off, off. This next sample here is that on, off, off, on, right? All right. So these are our samples, and these are these are the digital information that's going to be read. All right. So we'll take this graph. Take this little graph here, all right? And I counted them. There are 30 little arrows here, all right? So that's a 30 hertz sample, right? Because let's assume that the time that happened here is 1 second, right? If the time that happened here is 1 second, then this is a 30 hertz sample because there's 30 little arrows here. All right. How do we get a 4-bit depth? Well, there's 4 bits of information, right? There's 4 bits of information in each one of these. So it's a 4-bit depth. All right. So the sample rate is how often a signal is sampled when converted to a digital signal. If you've heard about MP3 files, a standard sample rate is 44.1 kilohertz. 44.1 kilohertz, or 44,100 samples per second. All right. So imagine there's 44,100 sample of these arrows in one sample, not in one sample, but in 1 second of sampling at that sample rate, at that MP3 sample rate. And the bit depth is the resolution of that sampling. Higher bit depths make for more accurate reproduction. So the bit depth here is 4. But if you've heard of 128 kilobits, that's a standard bit depth. That means that there's 128,000 ones and zeros in each one of the samples, representing each one of the samples. All right. So that sounds like a lot. It sounds like a high sample rate and a high bit depth, and produce really good sound, right? Well, it is and it isn't. All right. And we can get into the weeds about what's good about it and what's not so good about it. And we will in a second. But this whole process is called quantization, when we're taking this analog information and turning it into digital information. We talked about this, right, in our video about quantization. So when they were coming up with, what are these algorithms, what do they all mean? What are we going to do with them? There's this group of people, the motion picture experts group. They started classifying the different file types, right? And they came up with an algorithm that had subsystems for audio called MPEG, named after the motion picture experts group, MPEG. And they had MPEG audio layer 2, MPEG audio layer 3, and MPEG audio layer 4. We know them as MP2s and MP3s and MP4s, all right? There are all sorts of file types. You want to look up file types, the list goes on and on and on and on and on and on, right? But MP3s are one of that long list that we know of, right? Now, these are compressed file. We also look at the file types, and there are compressed file types, non-compressed, and lossless file types. And what do we mean by this? We'll start here with the non-compressed file types. Basically, when you have a WAV file, this is an AIFF, which is a Mac version of a WAV file. Sound Designer 2 for any of our Pro Tools warriors out here. That was a file type that Pro Tools used once back in the day, right? These WAV file types, they are non-compressed. And basically, when they are not compressed, it means that all of the information that was sampled when they did that sampling, and they did it at a really high bit depth and high sample rate, all that information got put into the file. All right, so that's non-compressed. All that information is there, but you can imagine that these are monster files. These are big files. So if you're going to store them on a computer or push them down the internet, it's going to take a long time. Pushing down the internet, and it's going to take up a lot of space on your computer. And what if it was a video file? It's even larger and larger. So they came up with all these compressed file formats where they figured out a way to take out some of the bits of information. All right, and I've got this one right here, MP3 11:1 stereo. And what this means is that for every 11 bits of information from the original file in your MP3 file, you've got 1 bit of information. Okay, so in your 44.1, 128 file type, MP3 file type, you are left with somewhere around 10% of the original file information, the original audio information. And they have figured out that that's an acceptable rate for most people, right? It's an acceptable amount of loss for most people. Well, that's great if you're listening on something like this, right? You're listening over your computer, you're trying to get something down the internet, you're trying to store it on a 4 gig hard drive or something like that. But we got better hard drives now, and we got better capacity on our internet, and we're getting better and better speakers. We went to this point where we had huge, great speakers, and then we started listening to everything out of earbuds and computer speakers, and it didn't matter. But if you're in post-production, it definitely does matter, because eventually in post-production, you're going to be doing things for 5.1 sound, surround sound. You're going to be doing things for theaters and large halls, and they have huge speakers, right? And nice speakers. So you need something better than a compressed format. So you can work in a non-compressed format, or you can work in a lossless format, which is basically a free lossless audio codec. And not to get you too much into the weeds, but instead of having only 10% left, you're left with anywhere from 40 to 60% of the original source audio. And so this lossless format, both Apple and Windows Media have their own free lossless audio codec format. You get more of the information. And a lot of places, a lot of post houses, they're using this for audio. Okay, so we've got non-compressed, that's a non-lossy format. Non-compressed over here, non-lossy. All right, just think of loss as you're losing some information, right? You're non-lossy, you're not losing information. The compressed formats are lossy. You're losing information. It's lossy, L-O-S-S-Y. And then over here, you have lossless formats, the FLAC formats, which means that it's somewhere in between your non-lossy and your lossy formats. It's lossless. All right. Okay, now let's look at the consoles, and specifically, we're going to get into our console that we have at De Anza. But consoles and mixers and consoles basically do the same sort of thing. It's just that mixers tend to be smaller things here. This is a mic mixer, so it's smaller, and it's just, you know, to mix mics in a situation. Consoles handle big mixes, right? And they handle main mixes and some sub mixes and the overall sound of a mix. Here's a big console for a concert. Here's a console that is in a post-production house. Here is a console that is actually in a TV truck. All right, wonderful. I would love to work in that TV truck, right? But we also have a console there in our audio studio at De Anza, right? Now, we can classify consoles also by their construction. Analog consoles are where you have analog signals, electrical signals, flowing through the wires, through all the potentiometers and faders and switches and circuits. Or you can have digital consoles, where somewhere when you plug that XLR cable into the back of that console, in that digital console, the console converts that analog signal into a digital signal, and then all of the signal that's running through that console is digital. And the good thing about that is that it's a low noise signal. The analog consoles can introduce some noise, but the digital consoles do not have anywhere near the amount of noise that analog consoles have. And so that's why we're going to digital consoles more and more. It was kind of a new phenomenon 10 years ago. Now it's getting harder and harder to find an analog console, although you still can. Now here's our production mixer, right, that we have in our studio, in our audio studio at De Anza. And this is the fader. These are the fader modules. So this is the fader module section, and these are the faders. We'll get to exactly going through each one of these, but this section is for the fader modules. Our next section is the output and monitor stage. All right. So this stage controls this is the output stage. So all of these fader modules eventually go to here, to this red fader right there, and that's the output, the final output. And this also controls the monitors. Remember, in video, our monitors are the pictures, are the TV screens up there by the director's location. Those are our TV monitors, right? Well, in the audio booth, the monitors are those speakers on the right and left, right? Those are the audio monitors. So the controls speakers. And then our other stage here is the mix control. All right. They did a really cool thing with our mixer. There's all sorts of great gadgets and knobs to turn in this mix control area. We'll go over a little bit of it, right? And instead of having all those great gadgets come off of each fader, which would make that board so big, it would make that board really long, and it would make it really, really tall. They did a thing where they have this mix control, and by clicking on the buttons up here, this mix control then is now controlling this fader. And then if we click on here, then this mix control then is controlling this one. All right. And so it makes the board, the console, smaller, also makes it a little cheaper. So that's also a good thing too. Okay, so here is the master section where the master fader is, right? So this is the output section where the master fader is. Now our board is a little strange. It's a little atypical. So you got to get to know this, okay? When this button right here is on, when it's pushed on, this fader is controlling the speaker volume. the monitor volume. So you push it down, and then you can turn up the speakers and turn them down. It doesn't affect the mix in the board. When it's off, when this is pushed up, then this is controlling the output. Okay, so you just got to be aware of that. So generally what you do is you set up the board with this, with the master volume at a certain place. And once you get the master volume at the place you like it, then you push it down and you control the monitors and you operate with the monitors that way, right? We're not really using TalkBack, but this is for TalkBack if you want to go down to the studio and talk to somebody in the studio. This is where we get our test tone. So when we're doing the tone and bars and tone, right, you click that down and you get that test tone. That's where that's at. All right. And here's our the fader module section right here. Right. So here's the fader. Right. This turns it on. So you want to make sure that the on switch is on. Right. And then typically what you'll do is you'll run it up. If you're going to set a tone for something, you'll run it up to 0. That's what they call unity gain. It's just a place that the engineers have set that this is where the optimum level. But if you want to run it softer, you can go down this way. And if you want to run it a little louder, you go up that way. Right. So this blue button up here is where we can select the control, the control part of that, the mix edit section, right? This is just for a cue speaker that's somewhere off the side of the board. So we got a problem here. We got a problem. Somebody downstairs says the microphone's not working, right? And the microphone's, of course, on this fader somewhere. Well, you can, first thing you want to do is you want to look up here at this section, because there's a VU meter right here. And if these VU meters are happening, then you've got signal coming into the board, into this module. Okay, so if these VU meters are happening, then well, maybe I need to turn up the module here, turn up the fader. And if that doesn't help, then I need to make sure that the master's up too. All right. If they say, oh, the microphone's not working and you don't see any meters here, well, then you need to go over to the receiver on the side, right, and make sure that the transmitter's turned on and the receiver's turned on and that the batteries are working, and see if you got any audio going through there. So this is an important meter to help you with diagnostics. That's the input. It always meters the input. And then we have the module, edit mix section, and you control that from here. So if we push this button right here, fader number 9 then would be controlled by this. You could do some settings on this. And what different settings can we do? Well, let's see. If we put this fader at 0, set this fader at 0, and then we hit the beep, hit the tone, and you want to get the VU meter tone to be right here where we've marked it on the board, right here to unity gain. When that reads 0, well, how do we get it up to 0? Well, there's this this potentiometer, we call them a pot, right? This trim pot, you trim it up so that the meter volume goes up to here and not past it, but right up to there. When that reads 0 and this is at 0, then you're all good and you've set the level for that, right? What other things can we do with our with this feature here? Well, we can also do things like set the pan pot. So that's right here. That is just the left, right. So on our microphones, you want to make sure the pan pot's right in the center, okay? And then we can do all sorts of other cool things. This is for EQ. And then we also have some compressors. We're not going to really be messing with them in class, but maybe when we get to the final production, somebody who has some audio chops might, definitely if we have a follow-on class, you would be using this, but right now we don't need to worry about that. So I talked about VU meters. VU meters are, VU stands for volume unit, right? And we have LED meters on ours, which means they use light emitting diodes. All right. It's not the needle meter, and they indicate different things. Since we really don't have any of these in our plant, you don't need to really worry about these. We've set a unity gain right here, and this is where you want the VU meter to go, right? Just be aware that on some VU meters, on the LED meters, you can't go over much over 0. When you go over 0, you start losing information. It starts over modulating really bad. So a lot of times -12, -10, or -12 is where we set it, right? And that's our unity gain on these VU meters, okay? And then we have some recording devices. This is an H4n that maybe you check out. Something like this is a portable recorder for field recording. We record on servers in the server room, right? Basically, we're recording on a computer. Here's some digital audio programs. This is Adobe Audition. Maybe you've seen that. It's like what Premiere uses. And then this is an older version of Pro Tools, and we have Pro Tools in our plant somewhere, right? In the Foley room, they're using Pro Tools, so you might be able to work that. And oh my goodness, all about sound and audio that you ever wanted to learn, and a little bit more, right? Well, this encompasses chapter 7. All right, be sure to take a look at chapter 7 in the book, and then go take the quiz and complete that for this module. Thanks.